Hello everyone, welcome back to Z Physics. What we're going to be doing today is carrying on with our series on the transition from GCSE physics to A-level physics. In particular, we're going to focus on two of the most important skills that we need to revise, and those are gradients and the line of best fit. Okay, so let's get started. We have a past paper question here from the 2018 OCR Exploring Physics paper, so a real past paper physics question. We have a graph with some data points which are fairly typical from an experiment. So when you do an experiment, you would measure some quantities and you would plot them on a graph. What the question is asking us to do is to draw the straight line of best fit on the figure and then determine the gradient. Okay, so let's get started. Now, the rule with drawing lines of best fit would be to make sure that we have an approximately equal spread of data points on either side of the graph. So what I need to do is take my ruler and align it in a way that there's approximately half of the points are on one side of the graph and half are on the other side of the graph. So let's draw our line of best fit now, like so. And if I just remove the ruler, we can see that it passes through most of the points, and there's about 1 point which is on the left of the line, about 1 point which is on the right of the line. So I'm reasonably happy with this line of best fit. Now the next step would be to actually determine the gradient. The important rule in this case would be to ensure that our gradient triangle that we've chosen is sufficiently big. It needs to be bigger than at least half of the graph in either direction of the page. In other words, I would always try and make my gradient triangle as large as possible. For instance, if I just took the gradient of this low portion of the graph, this will be insufficient. So we can see that I've selected over here some points with 4 volts across here. Then I've gone down across and seen what the corresponding point on the x-axis is. Okay, well, let's determine the gradient of this line. The first thing that we need to remind ourselves is the formula for the gradient, and if we just remember from our GCSEs, our formula for the gradient is, let's call the gradient m, is just change in y, which is delta y, divided by change in x, which is going to equal to y2 minus y1 divided by x2 minus x1. Now our final value of y, which is y2, and I've taken this point over here, so we're just going to go straight to the y-axis. We're going to see that this is 4 volts. So my y2 is equal to 4 volts minus my initial value, and for the initial point I'm just going to take this point over here, and I can see that this is somewhere between 0 and 1, so it's going to be 1, 2, 3, 4, so it's going to be at 0.4 volts. So minus 0.4, and I'm going to divide this expression by the x-coordinates of those 2 points. I'm going to need to be careful. Consider I've highlighted this over here because all of these points actually need to be multiplied by 10 to the power of 6. So that's really significant. In fact, whenever we're dealing with graphs in A-level physics, I really advise you to have a really good look at the units. First of all, make sure that there are no tricks in the units, such as this factor of 10 to the power of 6. Okay, but anyways, the x-coordinate of this point over here, if we go down, we can see that this point here is sandwiched between 2.5 and 3, and the midway point between them is just 2.75. So I'm just going to write 2.75, and then I'm going to include the factor of 10 to the power of 6 times 10 to the 6. Notice that my x1 in this case is going to be just 0 because the x-coordinate of my first point is 0, so my x1 is 0. Of course, we don't have to write the -0 part, however, just for completeness, I've decided to include this. And if we put this expression into a scientific calculator, we're going to get 1.3 multiplied by 10 to the power of -6 volt meters. Let's tackle the final question. It says, use your answer for the gradient to determine a value for h, which is Planck's constant, to two significant figures, and we're going to need to show our working. Now the first step would be to apply a y equals mx plus c analysis to our equation which we have been given. So what I'm going to do is I'm just going to write down the equation over here, which is that v naught is equal to hc divided by e multiplied by 1 over lambda. This is just this equation. Now underneath that I'm going to write y is equal to mx plus c. Because I don't have anything either added or subtracted from this expression, I'm just going to add a little plus 0. Now we're going to see that if we have v naught on the y-axis, which we do, so v naught is on the y-axis, we have 1 over lambda on the x-axis. Our intercept should be 0. It's not quite 0, it's incredibly close to 0, it's 0.4. However, that's probably due to experimental uncertainties and errors. So it's pretty close to 0. What we have left for our gradient is hc divided by e. So what I'm going to do is I'm going to say that this over here is our gradient. So our gradient m is equal to hc over e. Now in this case we're looking for a value for h, Planck's constant, so what I'm going to do is just rearrange for h. So h is going to equal to me divided by c. And now I can start plugging in some values. Our gradient from the previous part of the question is equal to 1.3 times 10 to the power of -6. The elementary charge, we know from our formula booklet, that's equal to 1.6 times 10 to the power of -19. I'm going to need to divide that by the speed of light c, which is equal to 3.0 times 10 to the power of 8 meters per second. And if we input that into a scientific calculator, what we're going to get is 6.9 multiplied by 10 to the power of -34 joule seconds. Now notice that here they were asking us to give a value for the answer to two significant figures. So just a quick check, the answer is given to two significant figures. Okay folks, so hopefully those skills make sense now. If there are any questions about gradients or lines or best fit, feel free to drop a comment down below, and thank you for watching.